All right, ladies and gentlemen, Do Not Disturb is on, so you know it's time for business. So today we're going to talk about the abbreviated electron configurations and briefly glaze over ion configurations in this little video here. So let's get started. First, let's go and talk about abbreviated electron configurations. They start on the same off-off principles of fill as we learned in class, but the abbreviated configurations benefit from a shortcut method. And that shortcut method has to do with called a noble gas core. We'll get to that in a second. But you need to make sure you understand this principle right here, Aufbau's tree of goodness. If you can understand that, then this is going to be pretty easy for you to do. There's just a couple more layers to it, and then you're good to go. It'll save you a lot of time in the long run. But dancing over to ion configurations here, when we're talking about ion configurations, you can imagine your atom looking something like this, where every orbital has some kind of specific appearance, whether it be this arrangement here, where I have these unpaired electrons here, or what have you. The arrangement can change, but the order of fill doesn't. And when we're talking about ion formations, you can imagine your nucleus is here, and it's surrounded by this cloud of electrons. Now we know that they're not fixed in these orbitals, but dancing in between them. But this is just for a visualization's sake. So if we take this ring, let's take this N4 ring, for example, and magnify it in. So like we're here, we're gonna get way up close. What we would see is this level of accessibility. What these are doing, these are shielding the nucleus from any kind of outside invasion from a electron. Now, what that means for us is if we want to form an ion, let's say I want to take one from this p orbital out into the environment, I'm going to take it to my outermost shell. That's where my electron's going to come from. When I make these ions, I'm pulling from what's available to me, my highest principal energy level first, in the SPDF order, like always. So then you'll use your off-box tree. So like if I have a 6s and a 5f, well, 6s is further out than 5f, so this is more readily available. So I would pull those electrons from this 6s orbital, and likewise, depending on what element you're doing from. It's this context of shielding an ion formation. When you steal from the outside in, you want to go with what's available to you first. Like if I'm an electron coming in looking to steal something or make a reaction happen, I hit this outer shell first, so that's likely where I'm going to pull my electrons from. Then I'll start from here, then here, and then rarely I'll get this close because that's a lot of positive pull happening right there. We'll talk about all of that later in the class. This is just general chemistry, so you're getting a gist or an overview here in the high school level. So we're talking our outside in, and what I mean by my outermost valence shell or outermost electron shell, that is called your valence shell. Your valence shell. Your outermost electrons are your valence electrons. Those ones are responsible for bonding and shapes and all of this goodness we will talk about in further units. But you just have to be familiar with that term of valence electrons. Valence electrons live in this outermost shell, whatever that outermost shell is. Now, sliding back to abbreviated electron configurations, you still steal from the outermost electrons even when you're using these abbreviated electron configurations. That principle still holds of electron shielding, so you must make sure you remember that. But in chemistry, we focus on certain exceptions, making that D4 and D9 elements. In this special zone, these ones will rearrange to make a more stable configuration, sliding from that outermost S, going from D4 to D5, and sliding from that outermost S and D9, sliding to a D10. All of that aside, we got to get started on how to start building these electron configurations shorthand or abbreviated. That way we can use them to help identify all of these special cases and whatnot, and we don't kill our hands writing. So I'm going to pick a color so you can easily see it. But on my standard off-boff tree, There's a shortcut to using your noble gas configurations. And I will backtrack and show you what a noble gas is. But I would encourage you to record this shortcut in the exact place you see it here. All noble gas configurations take part in P categories. They take part in P categories. And what that means for us is that all of these P orbitals you see on your Aufbau tree have associated noble gases that go with them. And that way, if we place them in the Aufbau tree when we're filling it and jumping off from our noble gas core, it makes the order of fill easier to see. When we're talking about noble gases are anything that exist in this here family right here, this column right here. These are our noble gases. They are highly inert gases, which means they do not react. They just exist nice and stable with 8 valence electrons, a nice full outer shell. But what that means for us is we can use them to annotate certain things. So abbreviated electron configurations use this noble gas core. This core, i.e. those elements in purple, they represent the electrons that they have. So like, let's say helium. Helium has an atomic number of 2. That would represent 2 electrons. Neon has 10, so that represents 10 electrons. Argon has 18 electrons in its ground state. Therefore, it represents those 18 electrons, and so on and so forth, all the way down the family from radon and down. And that core gives you a jumping off point to go further along in the story. Now, when we put that to use, I'm going to throw some flashbacks here. We did tungsten in class. Tungsten's full electron configuration is this wonderfulness right here. All 1,000,007 electrons accounted for. Notice that special case when we have tungsten being a D4 element right here. And we slide down to make that appropriate adjustment in our S and D orbitals. It's D4, so we know it steals 1 from that outer S orbital and moves it to D5 for a full stable configuration. We got to spread that love around. But what we can do is with these abbreviated electron configurations, we can represent all of these electrons in this red box. If we just use a xenon core, because xenon has 54 electrons, and what I have in red is 54 electrons. So the abbreviated configuration for tungsten would start at xenon. It would be xenon in brackets, and then since xenon represents 54 electrons, I'm going to start at 5p, and I'm going to move my way down. So I start here, and I start filling down. Then I come to 6s, slide back around and hit 4f, 5d, 6s, 7s, 5f, and 6d as I go all the way up to my my 74 electrons, not 54, my 74 electrons. And we keep counting and so on. So here we got 56 electrons represented. So then we're coming to 6s2. But we know it's 6s1 because it rearranges. So there's 54, that's 55. And let me be smart here. We said xenon is 54 electrons. Let me make my life prettier. 54 electrons plus that 1 I just drew, plus 14 more. I'm at 69 so far. I got to get to 74. So I'm going to keep going with that 5d5 plus 5. Boom, bow, that's how you do that. And I kind of gave it away when I showed all of the configuration, but this is an abbreviated form. It takes all of 56 of those electrons and represented by a noble gas core. The catch is when you're using an abbreviated electron configuration, you must always have an S following that bracket. Notice how when we filled it in, everybody's next person is always an S. So when you're doing these, a good way to check yourself if you're putting things in the right places is the next one is always an S. At least here in general chemistry. So it'll always be an S orbital. So based on what you know, I want you to give yourself a try using these examples here. We're going to go with scandium with 21 electrons and go on down the line. So scandium has 21 electrons, and I have to use my noble gas core, but I didn't specify how to pick a noble gas core. Your noble gas core can't exceed how many electrons you have. So if I'm doing scandium, scandium's number 21. So let's zoom in here so we can see. Scandium is number 21, so we're here. All right, I can't go forward and pick krypton. That would be too many electrons. For me to do the abbreviated electron configuration of scandium, I have to backtrack. For me to do it successfully, I have to backtrack all the way to my closest preceding noble gas, i.e. the one that comes before scandium. Scandium's right here, so I have to backtrack to my next available noble gas, which is argon at 18. And that would give me 18 electrons to work with, so I don't have to start out from 1, and then I can build off of that. I can't take them away, but I can add them. So you always use the closest preceding noble gas. So using the closest preceding noble gas. Always. Use your closest preceding noble gas. Same thing like with tungsten. Tungsten's here, and I backtrack all the way to xenon to represent those 54 electrons. Instead of sitting there and counting them up and seeing where I don't go over and whatnot, you can just remember the closest preceding noble gas, and you'll always be good to go. So scandium's closest preceding gas, as we've established, is argon. So I'm going to represent argon like so. Argon holds 18 electrons. So here I can go from argon. I know argon lives right here. And then I'm going to go down. So my next configuration will be 4s something. I know it should be 4s2. That's 18, 19, 20. I need one more. 4s comes to 3d. I need my extra one there. Now we're going to slide down here to antimony. Antimony has 51 electrons. That would definitely make your hand hurt trying to copy all of that. So with antimony down here, let me see if I can't change colors real quick so we can see it easier. Antimony being SB with 51 electrons right there. I'm going to continue to backtrack and backtrack and backtrack all the way until I get to my closest preceding noble gas. So I'm going to keep going, keep going, keep going, keep going. Merp. The next one would be krypton. So antimony's base is krypton. So I draw my base, krypton. Then I keep going. So krypton represents 36 electrons. So I need to get to 51. So 36. My next one will be 5s2. Then I'm going to come to 4d10. Then finally I'm going to have some left over here at 5p3. So all I do is I take my noble gas core. I've established its krypton. Then bloop, fill it like you normally would. Just like so. Now hopefully you can track that your periodic table has been sliced. So here is where your lanthanide series belong, and there is where your actinium series belong. So you can imagine your periodic table right here stretching out in both directions, becoming incredibly long. The reason they do this is these are lanthanide actinide series, or rare earth metals. So what they do is they splice them out right here and cut them down below to honestly save on printing. That way we can compress the periodic table into a more friendly version for us to use in textbooks and handouts and the like. But we just have to use the atomic numbers to appropriate where we're supposed to put things. So samarium is right here at 62. I know 62 is an lanthanide series, so that would be up here-ish. So I'm going to backtrack from where I'm supposed to be, and I come to xenon. So I know my core has to be at xenon. So samarium's core is xenon. And then we start filling. I come to xenon, then I know I'm at some 6s orbital. So because after every abbreviated configuration, after every core, comes some s orbital. And xenon represents 54 electrons. I know samarium needs 62, so I only got to get 10 more. 4f6. There we go. You just fill in like you normally would. And I just write it here for posterity's sake. So again, it's your closest preceding noble gas core, and you just build your configurations like you normally would, jumping off from that noble gas, which represents that many electrons. It's pretty easy and straightforward. Now you can even turn these into ion formations where, you know, let's say I want to do the abbreviated configuration. That is ugly. Hold on. Eee. For, I don't know, off the top of my head, let's do chlorine. Sure. Actually, we're going to do oxygen. So you got to compare it. So oxygen in your ground state is 8 electrons. So I have a total of 10 electrons cooking. So my closest preceding, so I have 2 extra here annotated by that negative charge. So my closest preceding noble gas from oxygen would be helium. Helium represents 2 electrons. So I'm going to slide up here and start my configuration. So I come to 2s. So it's 2s2. So there's 4 electrons. 2s2, 2p. Let's see. I have 4. So here we go. 2s. So there's 2, 4. Now I come to 2p. Now I got to figure out how many go in 2p. I know I have a total of 10 electrons to account for because oxygen has 2 extras with that -2 charge on it. So that is 2 electrons right there. There's 2 and 2 make 4, and 4 and 6 would make 10. So there we go. I'm going to make that nice and pretty. All done. And as you can see, it works the same. All you gotta do is count electrons. It's pretty straightforward once you get to doing it. It just saves you a lot of time when you're building these configurations. The catch is you have to have a strong understanding of Aufbau's principle and where your shortcuts are. Because if I count up these electrons, I know an s orbital can hold 2 electrons. And then each s orbital can hold 2. And a p orbital can hold 6. 2 and 6. And all you gotta do is count up. So 2 electrons, the thing that looks a lot like 2 electrons with 2 protons is helium as a noble gas. Then 2 plus 2 is 4. 4 plus 6 is 10. A thing with 10 electrons is neon right here. Then those 10 plus 2 more is 12. 12 plus 6 is another 18. That's 18 electrons in argon. And you can see how this kind of builds on itself. So even if you can't remember where it's placed, the backup system is you just got to count. But it helps to know that all of them should be in the P zone, and then they follow the S. And if you don't remember your zones, let's get some colors going on here. Everybody I'm about to color in red is a part of your S orbitals. And don't forget our helium counterpart over here. That is an S orbital as well. Then you got what's going to be in green here on this little block, because everything in this block is a P orbital. Then in the middle, you got your D block. Everything down here should end in a D configuration, which is what we see when we do D4 to D5 and D9 to D10. And everybody way down here is an F block. So everybody down here has an F configuration at the end. So that's how you can kind of check yourself where your zones of elements are. You kind of look where it lives on the periodic table. And like, okay, so if I live in this area right here, like let's say arsenic right here, I know arsenic should end in some kind of P arrangement because it's in the P zone. Same thing with sodium. It has some kind of S configuration at the end because it's in the S zone. And same with F and D, because like we know chromium has a 4D to 5D configuration because it's in D block, and it's D4 because 1, 2, 3, and 4 right here. We know it should switch around that last S orbital, but we know it ends in D. So that's how you can visually check how your configurations are going on based on where the electrons live on the periodic table. And that's pretty much how you do abbreviated configurations. You just count and follow the rules of off-box order of fill. If you have questions, y'all have the email. Have a wonderful night.